Okay, so firstly, let's welcome our very hardly reached here speaker, Dr. Jeremy Fishel. So Dr. Jeremy Fishel is a co-founder and the chief technology officer at Syntax. So as most of you may have heard of, the biotech sensor is from their company. And his professional interests are in pioneering applications in tactile perception and robotic dexterity using Syntax core technology. So today, he's going to give a talk on the application in touch with focus on dexterity and perception.
Is it blue? Yeah.
Each talk is actually 25 minutes. So we do start from there, Okay. 25 minutes, not
Jeremy,
30 minutes.
you want to try a different connector?
Yeah, do you have one? I think this one's messed up. It's the new Mac one.
Well, I don't know if the new Mac is going to match this.
No. Start from restart.
But this for emergency.
So this should be 20 minutes. This should be a 24 minutes. And then we'll have 5 minutes question.
Oh, it's this. But I don't have a little jumper for it.
Alright.
Oh, you can see it. Now I need an HDMI cable.
It's there, but it's not so, the length of the
Want me to go over there?
that's the maximum.
It's like Back to the Future.
I'll talk to him over here. Oh, yes, that's it.
Yeah, awesome. Yes.
So sorry for being late. I landed at 2 a.m. So I'm Jeremy, the CTO and co-founder of Syntax. We were founded in 2008 as a spinoff from the University of Southern California. We're based in Los Angeles, and we focus on developing human-like tactile sensors and new applications of what we've been calling machine touch. So normally I spend a good chunk of time talking about our core technology. We're famous for the green biotech fingertip, which is now in the right colors. I normally talk a little bit about the biological transducers, cutaneous and proprioceptive touch, how in the artificial domain, strain gauges and position encoders are covering the proprioceptive touch quite well. However, in the cutaneous domain, most people have been focusing on high-resolution normal force sensing, which is more like human vision than like human touch, which is more force, thermal, and vibrations. And how people aren't even good at high-resolution normal force sensing, and how we've made a green robot sensor that can do all of these things. But today's talk, I want to focus a little bit more about applications of tactile sensing. So I'm going to tell a story I haven't really told before about our early research back in 2008 when we had this new green sensor and ugly logo. And we were really paying a lot of attention to this relationship between decision making and perception and action. And specifically the relationship between action and perception, so action for perception, making exploratory movements to collect data about what the world feels like, as well as perception for action, where we use tactile data to intelligently control reflexes. So we had the cool green sensor. There were a lot of interesting hands that had some good dexterity to them. But the decision-making part, the brain and artificial intelligence, we decided was a really, really hard problem that we didn't want to mess with as we're trying to learn all the applications of tactile sensing. So we had a pretty clever solution, which was to just use amputees. We could use their brains, our sensors, robotic hands, and study how touch can be used in different applications. So just a quick overview of how our vision of things work. You start off with a task in the brain, or your motor plan about what you want to do. Your spinal cord, which is sometimes misconstrued as just a cable that connects between your brain and your muscles, is actually doing quite a lot of active control about what's going on. It sends signals to your muscles, which move your hand and fingertips. Everything in your environment can be perceived with visual and audio feedback. And the tactile feedback has two different pathways. One of them goes reflexively back to the spinal cord. This is a perception for action, being able to detect something and respond to it intelligently. And the other one goes straight back to the brain for perception. What am I touching? What does it feel like? So in the unique case of an amputation, if you had transradial amputation, you start losing, obviously, your hand and some of your muscles. And one current intervention, which people are hopefully familiar with, is myoelectrical control. So in this type of intervention, EMG signals are recorded from the residual muscles. They can be conditioned in such a way to be proportional to activation force, driven to a controller, and then drive the prosthetic hand. Now, in this type of scenario, the prosthetic hand and the environment and what's being grabbed can only be fed back with visual and audio. So you're not able to feel anything that you're touching. And we're missing those two key feedback loops, right? We've got the action for perception for our perception, and perception for action, which gives us the smart reflexes. So one of the first things we looked at was we had a great sensor that could do force, vibrations, and temperature. Let's play back forces and vibrations and temperature straight to the amputee and see what they can perceive. Now I want to point out here, we made some very basic technologies to vibrate, heat, and push on the skin, fed it back directly to the skin, so no neural intervention here. And that's a popular thing in neural prosthetics, is taking this information and plugging it back into the brain. But one point I like to make is that if you consider like a retinal prosthesis where people want to stimulate the residual retina, these are people that have no other way to perceive light. And a cochlear prosthesis goes to your ear where there's no other way to perceive sound. So, your body's covered in skin. So why go to the nervous system when you could literally just stimulate skin elsewhere, which has already been conditioned to transduce these different stimuli into proper neural code. So that's the thing that we've been fond of doing. We stimulated direct to the skin. It actually worked fantastically well. We had outstanding discrimination in terms of this soda's been out of the fridge for 10 minutes, this one just came out of the fridge. Different textures on maybe 5 different levels of roughness, gram resolution on some forces, like fantastic feedback for discrimination. And when you ask the amputees, they don't care. It turns out, if you start talking to the customers and learning about what they want, the main problem with amputees is they want to just grab things and not think about it. If you're a unilateral amputee, which is like 95, 99% of them, they have another hand. If they want to know what something feels like, they're going to use that. They just want their prosthetic hand to grab things. So, yep. We ultimately, that became foundation research we found a really good market that people did care about perceiving touch, and I'll get into that a little later. The next thing we looked at with the amputees is smart reflexes. So we looked at 3 different things. So we started off with some of the famous slip detection research. Essentially, our biotech can detect little vibrations. We can code it to determine if an object's slipping. That didn't work. It worked. It could detect if things were slipping and grip harder, but it also would misclassify any kind of dynamic event. And sometimes you want to slip. If you want to pass an object between 2 hands, slip is normal. So what we found specifically for the prosthetic market, which has very limited channels of control, the ability to, or the lack of ability to modulate the state, like now I don't want slip detection to work, made it really unusable. It sort of had a mind of its own, and it kept firing at unexpected times, and it made the amputees rather nervous to even use it at all. So undesirable. Same reason force cones didn't work, where this concept is if you detect an increase in shear force, you increase the normal force to maintain friction. Our biotech sensor can do normal and shear forces. That also had a lot of sort of mind of its own behavior that was undesirable. But instead worked really well is contact detection, and I'll get into that on these next few slides. So kind of some of the applications in touch that we're working on currently right now in the perception for action domain has a lot to do with contact detection and collision mitigation. So has anyone ever kind of taken a step back to ask themselves why all today's robots, arms and hands, tend to look like giant insects with an exoskeleton, is what I mean. So I want to talk a little bit about what biologists call allometry, which is sort of the study of how things change on different sizes of organisms. So there certainly are a lot of biological animals with exoskeletons, insects, crabs, spiders, which I think is an insect. And what's important to understand about exoskeletons is the mass of the exoskeleton goes up with the length cubed of the object, while its strength of the cross-sectional area is the length squared. So as things get bigger, they need to move slower or they will damage themselves. Unless you follow what nature does and you put the squishy stuff on the outside and you have a way to detect and respond to the collision before the forces get too high. So I think there is a recent example of this with Rethink Robotics. They used a large exoskeleton robot that can do some very interesting tasks. It's about 100 times larger than insects, moves about 10 times slower than a person if you could ever see it going live, which means in an industrial setting, you need 10 robots to replace one human's performance, and those 10 robots may need a human supervisor to keep after them, and now you've just replaced one human with 10 robots and a supervisor, which makes no financial sense unless you can speed up the output and autonomy of this robot. And indeed, most industrial applications tend to put the robot in a cage, where you can almost guarantee that it'll never collide with anything. So one key point, respect nature, put the squishy stuff on the outside when you want to make things big if you want to go fast. So we've got squishy sensors, we put them on the end of a prosthesis. Now we've got to ask this question, how do we get this tactile information back into the spinal cord? So as you might have guessed from earlier, I'm not a big fan of neural interventions that aren't necessary. So we started asking ourselves, sorry, that's not there. What would this EMG signal look like if this pathway were in place? And what we created was a spinal-like regulator that would take the EMG signals, modify them directly based on tactile sensing, and produce a modified EMG that would otherwise look like what that full pathway is. Now, in prosthetic hands, this is important because amputees want to have strong hand, fast hands. The Autowalk Very Plus speed goes at about 30 centimeters per second with 100 newtons of crushing force. And those strong hands require big currents, and when they stall on objects, they crush them, about 40 to 100 newtons. Now, it is possible to grasp objects with like force, but it requires visual feedback and a high degree of attention. And outside of experiments where people are forcing people to grab fragile objects, they don't do it in the real world. So we try to ask, can we have quick and fragile grasping reflexes? So we started off with using our biotech sensors to detect contact, and we very simply just reduce force on contact to prevent crushing. Very simple system. We took the EMG sensors and the tactile data from our sensors, fed it directly to a PC, ran it through a buffer, and drove the motors based on the algorithm I showed before. Our reflexive method works similarly to an inhibitory reflex. So before contact, we have unity gain on this red curve. This would be the raw EMG coming in and the modified EMG going out. But when we detect contact, we have an inhibitory effect that reduces the gain on contact. So if you were moving at this force and you make contact, you can quickly drop force and not crush the object. Yet we still allowed the ability to reach high forces, and you could crush objects if you wanted to. So a few years ago, we ran a couple of quick experiments with 3 different fragile objects. We've got foam peanuts that break at about 3 newtons, crackers that break at about 10 newtons, and eggshells that break at about 25 newtons. And we looked at 4 different states. We asked the subjects to use their dominant or sound side hand to move objects. We looked at their personal prosthetic, which was very plus speed. We looked at our performance with just the compliant fingertips, because arguably the compliant fingertips without any reflex could offer benefit. And then we also looked at it with the contact detection. So here's a quick side-by-side demo, if I can start this at the same time. So on the right, we've got contact detection working. On the left, you can see the visual attention, moving very slowly, sometimes crushing an object, sometimes dropping an object. That was by chance that I grabbed that segment, so you crush and drop right after each other. Much more difficult tasks. So looking at the data with this reflex, I'm just presenting a few for the crackers and foam. From the left, we've got their personal prosthesis. This is the no contact detection with the compliant fingertips, their compliant fingertips with contact detection, and then their dominant hand. And as you see, in all cases, the compliance adds benefit. And in fact, for a more rigid object like crackers, the compliant fingertips alone add a lot of benefit to speeding up the task. But the contact detection, in particular with more fragile objects, offers a lot of performance. It starts approaching the dominant hand quite quickly. Now, as we did this and started watching the users using the hand in a more natural environment, we realized that the speed alone wasn't the benefit. But if you note right here, these are error bars between trials. The contact detection algorithm dropped the variability in performance down tremendously. You can see even though high here, it's still higher here. That variability is what allows the amputee to trust the task and not look at their hand. If they don't trust it and know how it's going to behave, they have to look at their hand and pay attention to it. And in fact, our experiments right now are looking at how much visual and cognitive attention are affecting the task in these different scenarios. So I think I have time for this. The way we view dexterity is not necessarily having a high degree of freedom robotic hand, but I view dexterity as being responsive to uncertainty and unexpected events. So humans manage manage uncertainty with tactile information and visual information, and certainly amputees without any tactile information with visual feedback. Now this is some research from Veronica's PhD advisor, where able-bodied subjects were to perform a task where it's an unstable spring, right? You can see in the top left. And the idea is if you push too hard or deviate offside, it'll buckle. So the measure of performance in this task is how much force can you produce without the spring buckling. And they looked at a few cases. First, they started off with subjects without vision and anesthetized fingertips. There's still some proprioceptive information in the muscle, but you get some baseline performance of how much force they can produce. Next, they look at the state where visual information is available, but still no cutaneous information, and we see a significant improvement of that. The third case, we see tactile information, but no visual information, and we still see a significant improvement over tactile information. And in the final case, where we have tactile and vision, it's statistically similar to tactile alone. So my takeaway from this is, certainly if you have nothing, vision's great, but for some tasks, having tactile information is what's necessary to be dexterous. And we had an opportunity to test this. This is Vikram, who's been our subject for a while, using a prosthetic hand with no tactile sensing but vision, and no vision but tactile sensing reflexes. So initially, he's got to figure out where everything is. But then after that, on the left, it gets going pretty quickly. It was kind of gratifying to see that kind of performance that we saw where tactile sensing can dominate vision. Yep. You guys get the point. So currently we're working with different prosthetic hand manufacturers. We've got grants with the NIH and DoD, and we're taking these hands to do clinical studies to evaluate how cognitive and visual distraction affect the task, as well as take on studies to see if we can improve usage and potentially actually save power because the hands aren't getting to as high a force. And then there's Vikram's 15 seconds of fame on the Today Show. Now the other domain, applications where we have action for perception. So we make exploratory movements to perceive the environment. So we started asking ourselves the question, how do people perceive touch? And can we design an instrument to do the same thing? So there's a lot of instruments in the tribology domain that can tell you a lot about engineering properties like friction, surface roughness, but not about human perception. These tend to be very precise and repeatable, but not relevant to what people perceive. On the contrary, most industry applications for evaluating what things feel like tend to incorporate sort of expert feelers, like expert tasters or expert wine testers that are trained to identify what things feel like. Certainly very relevant properties, but not very precise. There's variability between subjects and day to day. So we sought out, can we get something that's precise and repeatable, yet very relevant to human perception? So about 5 years ago, we did a pretty big paper we call Bayesian exploration for texture discrimination, where we looked at 3 different dimensions of touch, sort of roughness, friction, and coarseness. Since that, over the last 5 years, we've now incorporated a much bigger product that has 15 different dimensions of touch and makes more exploratory movements and is more comprehensive. This study, we used about 100 surfaces at 95% discriminability and exceeded human performance. Now we've got about 8,000 surfaces unpublished and are blowing away human discriminability with about like 99.5% discrimination ability. So there's sort of a couple of key ingredients to this. So obviously having human-like tactile sensing is relevant to sense information like people would otherwise feel when they touch objects. We need exploratory movements that are similar to ones people would make to elicit that same kind of information. And we need to look at the neurophysiology to try to derive some intelligent signal processing to get relevant information. We end up getting about 15 dimensions to describe the way things feel, and we kind of pitch it as like Pantone for touch, if you guys are familiar with that. It's like RGB for touch. So one key point to make about perceiving things, it's really important to understand the perception of what you feel is just as much of a property, the mechanical properties of your fingertip, as it is the object you're touching. There's two parts in this interaction, and if you don't have the mechanical properties of the fingertip, the interaction will not be like what people feel. So we've got similar mechanical properties in the biotech. It's very deformable and compliant. Always work for improvement here, but it's still pretty good. Also, obviously, the perception of touch is going to be controlled by the movements that you make. So obviously, if you don't move, you don't feel anything. So how hard do I push? How fast do I slide? All of these questions need to be asked. One of my favorite quotes from an old piece of literature from David Katz, it's almost a century old. He says, the tactual properties of our surroundings do not chatter at us like their colors. They remain mute until we make them speak. Eye movements do not create color the way finger movements create touch. So now we got to start asking ourselves the question, how do people decide which movements to make when they're feeling objects? So if I were to give you an unknown object, say it's a brick, what movement are we going to make? Are we going to slide our fingers? Are we going to push it? Are we going to tap? Are we going to rotate it? Are we going to heft it? And there's not only that, if I want to slide over it, there's parameters. How much force? How much velocity? How much do I accelerate? It gets to a point where doing every single exploratory movement becomes incredibly impractical, if not impossible, in classifying an object. So, jokes like, just a lot of math here. We came up with a pretty good algorithm to figure out, like a genetic algorithm, to take a lot of different test data and distill it into the most useful information, and came down to like a subset of 5 different exploratory movements we make to get the most information. I could talk about this for like an hour, but I don't have an hour. This is new stuff that I haven't presented anywhere. So here's kind of our framework of all this. We've got this tactile taxonomy. So you've got tactile perception, and this sort of breaks down into the surface properties as well as the geometric properties. So you can think of the surface properties as the color, and the geometric properties as its shape. You know, what's its shape, mass, its function, is it a button, is it a switch? This stuff's all really hard. So we've been spending 5 years looking at just the surface properties. So only look at flat surfaces. And what this comes out to be, we've seen about 80 different projects for customers where we get some really complicated surfaces, and we start building out these simple categories of touch from texture, grip, deformability, and cooling into, sorry, got ahead of myself. For these properties, we look at the language people use to describe objects, and then we start looking at the movements experts make, and then we start thinking about, from a neurophysiological basis, can we come up with a way to calculate this, and then we try to implement that into our sensor, and we use our AI algorithms, genetic algorithms, to validate if it works. And sort of here's the stuff I haven't shown before. This is our current taxonomy based on what we've learned. It's a hierarchical relationship. So, for example, if the surface doesn't have any deformability, it's not going to have any damping properties or local deformation. But as we start dealing with more and more customers and more difficult tasks, we start building out more and more nuance in this tree. So we've got different properties of texture, sort of this gritty, grainy, lumpy, or the spectrum of how big the particles are. There's this prickly dimension that sort of has an itchy feeling to it. How coarse or fine a surface is, if that coarseness is regular, is it fuzzy, does it grip, does it have any resistance when you're sliding? All this stuff we keep building out. I think we're up to about 19 dimensions in this next revision that they're going to let out. So that's where we are. Was 15, it'll be 19 pretty soon. So about 2 months ago, after this product was launched, I started focusing our research and development into new applications. So we've got all this way to characterize what things feel on 15 to 19 different dimensions. Can we play it back? So I've been looking into different tactile displays. We've got the information. What are the capabilities of these things to produce realistic sensations? And that's sort of the idea. If we kind of have a library of textures that can be used to drive realistic tactile displays, we work with a lot of key partners in the VR and telerobotics industries to characterize their displays and see which of our dimensions they can actually pay back and come up with the mapping so that we sort of can become the RGB or the language of touch to communicate this information. So, smart reflexes and good tactile displays that feel like real things. And here's where it all kind of comes together. So this is sort of actually our business model side. All of our market pool of money came from industry customers that have big problems in quantifying what surfaces feel like. Say, for example, you want to design a dashboard cover that feels like it's expensive but is otherwise made of cheap materials. We have tools to characterize what the expensive materials feel like, what the cheaper materials feel like, and guide their development so that we can have a high quality, low cost thing, because you don't want to sit in a car if it feels cheap, you don't buy it. So this is where we get most of our support from. Now we're looking at, can we use that data to drive displays? We're also in parallel looking at the perception for action side for smart reflexes, and these two things, realistic displays and delicate interaction with smart reflexes, naturally converge on having smart telerobotic systems where you can effectively feel what the robot's feeling, but due to the latencies of communications, the robot has some autonomy to do intelligent reflexes in between. So that's kind of the quick summary of what we're working on. Any questions?
Thank you, Jimmy.
Yeah, okay.
So, two quick questions.
Sure.
One is, you guys are very high end.
Yeah.
When are you going to go low end and serve the Facebook experience? The second,
I can't talk about that.
the second question is, you're all about fingertips,
Yeah.
and to serve the Facebook experience, you're going to have to get something more.
Yeah.
Maybe palms, maybe shoulders, maybe the whole body.
Sure. No, that's certainly an important direction to go. We've focused all of our R&D on let's get a sensor that has everything so that we can understand what the requirements are for the applications. So one example of what we did in prosthetics is we've got this fancy sensor that does force, vibration, temperature, but the only thing useful was just contact detection. So we redesigned a low-cost sensor made out of foam that just does contact detection. And that's the Pneumatech technology that I didn't present on. But that's currently what we're developing for these take-home studies. And it's the idea that can be made the cost that anything foam can be made in, just injection molded foams. Whole body would probably extend from that same concept. You need to probably have something moldable rather than buildable. These biotechs are built by hand, and changing their shape requires a lot of R&D effort. In fact, that was our design for about 9 years, and it took about 6 years before we redesigned it into a shape that was just this size, because it's a lot of effort to change its shape. So it had to be very application driven. But I think we know what's important and different ways to do things. So if there was an application and a business opportunity to do that, I think we've got good ideas in that direction.
Any more questions? Yeah, Dave.
So maybe not the 1 hour version, but at
Sure.
least the 30-second.
Yeah.
What exploratory movements did you end up deciding on? So the product, what exploratory
Yeah.
movements does
So
that
there's
do?
a few sliding movements and a few pushing movements with different parameters. So the sliding movements, there's some really, I'll talk to you about this more, but there's some really interesting stuff. If you've got force and velocity, force times velocity is power. There's some interesting stuff in like an isometric power domain, so low force, high velocity, high force, low velocity, that are really useful for separating things. So we've got low force, high velocity, high force, low velocity, medium force, medium velocity, and then we've got different combinations of pushing movements. One is sort of like a push and hold, like you would do for a thermal movement. The other one's sort of like dynamic push that you might get for compliant properties. Now all the parameters of that have been pretty highly tuned. You can keep a little proprietary because we spent 3 years finding them. Yeah.
Are you looking for the tactile stimulus adaptation also in this sensory mechanism?
Tactile what?
Adaptation, temporal adaptation means are you also, when you are exploring something,
Yeah.
are you also looking how we adapt our stimulus generally?
Yeah,
change our
that kind of stuff
sensitivity.
is for like really long interactions, sort of like subtracting background noise. This actually does come up when we deal with really noisy robotic hands that vibrate themselves.
Yes.
So we pick up all those very sensitive vibrations. So if the robot hand's vibrating, we're picking that up too. And we tend to use that as background noise that we subtract from when we get a contact event. That
So
answers that.
if that improves the performance of discriminability,
It reduces false positives. Obviously, the smoother the motion, the better.
We have time for one more question.
Yeah.
I noticed so you said you got down to about 5 exposures needed.
Yeah.
Tactile touch. Did you find they were quite similar to human exposures?
Yeah, for the most part. There's some mechanical distinction, so we've organized our, like people when they explore surfaces tend to go in circles and they rotate their finger around while they're doing that to make sure the fingerprints are perpendicular to the sliding motion. Now, in our new sensor, the fingerprints don't have this U shape anymore, they're just straight, so we just go back and forth so they stay perpendicular. We have found some instances where I think we've got to add to it as we get more nuanced features. Maybe talk more about that offline.
Thank you.